recording. So we have now moved on to rotation, and we get an introduction to our rotational variables. If I can find that pen. You'll remember last time we introduced our new variables. We want to get a good color going here of theta, right? Omega, and alpha. All right, where this was angular position, angular velocity, and angular acceleration. Now remember, we could express these two as vectors, but because theta, angular displacement, depends on the order of rotation, it's not really a vector, so it doesn't transform like a vector. So we have to keep that in mind when we do that. And I'm just reminded of a conversation I had with one of my old mentors this summer, actually. We were arguing about the, we find that in thermodynamics, sort of pseudo-vectors become vectors. We can make things that don't look like vectors transform into vectors. I don't think any of you guys will come across that particular, that level of vectorness, but we started arguing about whether we should teach you guys vectors in this class. He's a physicist, obviously, as well, and I think delta theta would be where if we have an argument, if we take up this argument again, we'd want to look at angular displacement in terms of the thermodynamic quantities we were talking about. But anyway, that's an interesting aside. It's something to think about. I guess what I'm going at here is you should understand that sometimes things can look like certain quantities, like vector quantities, but not be vector quantities, and I'm hoping that with this class, in your science classes, I think one of our goals is we're really trying to get you to not just accept what we say, right? Like you shouldn't be going through problems because, well, the professor said do this, 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 and this. You should be thinking about these quantities, and I'll tell you what they are, but you should be able to hopefully, and again, we're learning. You shouldn't have it mastered right now. But hopefully by the end of your education, you'll be able to go, well, wait a minute, is that really behaving like a vector? You'll ask these questions and know that the answer to those questions limit what those quantities can do in your model or when you're looking at something and how they can relate to other quantities. So I'm hoping that big picture aspect starts to become clear, and looking at something weird like delta theta and then taking its derivative and getting these vector quantities is interesting, because now, an interesting question is, are you taking a vector derivative, right? Are you doing a d? How is it that when you take a time derivative of a pseudo-vector, this gives you maps to a vector? I got to be honest with you, I'm not sure how that mapping looks like, and I've taken a lot of math. So that's a weird one. That's a weird one, because usually when we take time derivatives, that won't turn. So it's not a scalar either. That's the thing. It's just not a vector. So there's probably some sort of dot product. Well, no, because time's not a vector, but maybe there's a dot product with the operation and the quantity. Oh no, wait a minute. That's not how we get this. We don't take the derivative. No, we do of delta theta. We take d dt of theta rather. It's something to think about. It's something to think about. But I don't want to get too sidetracked. So we have our new variables, our rotation variables. We'll concentrate on those. And what we can see, to get things back down to a simpler level, is that those variables, right, which we have down here in our chart, you'll notice that under the assumption of constant angular acceleration, we could make analogous kinematic equations by using our equivalent linear variables and just sort of replacing them, right? You'll notice we have our chapter 2 equations with x's, a's, v's, and t's. And over here we have omegas, alphas, and thetas, and still t's, but they look the same. And what I'm really hoping this shows you too is that is how powerful that assumption of being constant really is, right? Because the form will look the same no matter what you're looking at if the second derivative of your position is constant. And you can see that you get the same constant acceleration kinematic equations. These are constant angular acceleration, these are constant linear acceleration. All right, and I want to emphasize that because some books, and it's very irritating, will call these standard or universal or make them seem very general when in fact they are very specific, and they assume they have an overriding arching assumption, which is that the acceleration is constant, and then it's a consequence of that. Okay? So I wanted to start with the cockroach checkpoint because everyone likes merry-go-rounds, and we've probably been missing our cockroaches. No, wait a minute. We were supposed to be at the cockroach checkpoint. Because we did this checkpoint yesterday. But we'll review some other things. We can relate our linear quantities to our angular quantities. And I remember we did this yesterday. All you have to know is the arc length here and related to circumference. It should be very intuitive. And then all you have to do is take the derivative to get the other. Well, yeah, I can go back, but you know, you also have it being recorded too. So they've already, in essence, been screenshotted. So. All right, no problem. So let's see. So we have our linear quantities relating to our rotational quantities, right? And we can go down the list and just take the time derivative, and it's pretty easy to get those equations, which we did yesterday. So I'd say go back and look at yesterday's video. And then we saw that we can have a tangential acceleration, which is different than our rotational acceleration. So we can look at general circular motion, not uniform circular motion necessarily, that will have the radial component we're used to for uniform circular motion, and this tangential component to acceleration as well. And you very much will see that the acceleration of something rotating like this, the magnitude of that acceleration will be equal to the square root of at squared plus ar squared. So they are vector components. You have to treat them like that. Okay? All right. So now we want to start with this problem. So a cockroach rides the rim of a rotating merry-go-round, so or a carousel, or however you're imagining it. If the angular speed of this system, merry-go-round plus cockroach, is constant, does the cockroach have A, radial acceleration, and B, tangential acceleration? And if omega is decreasing, does the cockroach then have radial acceleration and tangential acceleration? So we want to look at that. So what do you so look at the terms and try and work it out. Oh, I didn't turn on the video. Look at that. There, you can see me talking the small thing in the bottom now. No, having a hard time with this one? Good. Good. So while you're working on part C and D, let's take a look there, and hopefully this will help. This is, I like this one because it's mostly conceptual. All right. So if omega is constant, right, then d omega, this implies that d omega dt will equal 0, equals alpha, right? So if alpha equals 0, a tangential equals 0. And then we're in uniform circular motion, right? Right. But we're only looking at A and B. So far we still have to do C and D. But if we look here, right? Because remember AT, the tangential acceleration is going to equal alpha times r. All right. So if AT equals 0, we're in uniform circular motion. So I'm going to call that uniform circular motion, UCM. That's what that stands for, uniform circular motion. And then we can have that AR will equal V squared over R, and AT will equal 0. So that's where we get the yes, no, right? Because we'll certainly have V, R we'll certainly have an AR, but we won't have an AT. So now, that's A, or that's A and B. Now for C and D, right? We want to look here and we want to see, well, now d omega, we have omega is decreasing, so that means that d omega dt is going to equal alpha. Alpha will be slowing down, right? But alpha will not be 0. So what does that mean? How does that change things? Well, you should be able to see that AR, you're still going to have an AR, right? But now you're not in uniform circular. Now you're not in uniform circular motion anymore, because you'll have AT will now equal alpha R. So this will be a yes, and this will also be yes. Keep in mind, you're not being asked to solve for the actual radial acceleration here. There's no math. You're just identifying whether you have a certain property or not. And in a lot of ways, that's a far more important skill than being able to solve simple math. Okay? So any questions about this one? Think about that for a minute, because I didn't get as many answers as I usually like for this one. So I'm hoping that you have some questions. So there's no free body diagram for this. We're not talking about forces. If you want to look at it in a picture, a much better picture is, I'll draw a circle, but the free body diagrams only tell you about forces, and free body diagrams really work. We're starting to get to, with a free body diagram, we usually approximate them as a point. So we're going away from the usefulness of those free body diagrams, because we're going to be talking about rigid objects. So where the force applies on the object will make a difference when that has a fixed rotation. Now, if we have a circle, and I'll draw a circle. Let's make it big, and let's move that circle, because that's going to be, So I'll make 2 lines of different colors. I can try and give you some insight here. So let's pick this point here. The radial acceleration will just point in towards the center of the circle. All right. However, how to pick a color, we got to get over here. However, the tangential acceleration vector. No, I almost had it perfect, and then my pen, that's irritating. I have to delete it. It's not going to work. Sorry, I'm a little anal retentive about this part of it. There we go. And so this will be the tangential acceleration. All right, so let me go, we'll call this AT. And this will be AR. So this is the radial acceleration, and this is the tangential acceleration. All right. So the question when going back, I hope Chica that makes some sense, or at least that's a drawing, a diagram of where these acceleration vectors are going. The net acceleration might be, you're gonna make a parallelogram and add those together. But then in this case, you have non-uniform circular motion when you have AT. So you can't, if you're going around with a constant speed and uniform circular motion, by definition, omega is constant and there is no tangential acceleration, and you just move in the same velocity as a circle. But if you slow down, and you might stay within the confines of the circle with a net acceleration, but you might be speeding up or slowing down. Okay? So I hope that makes some sense of it, and I hope it makes it a little easier to see. Any other questions on this one, or clarifications? It's not a nice day out today, that's for sure. Okay, so I think I'm going to go on then but we're not done with examples yet. So we have another one for you guys to work on. And again, we have our answers. And again, I think we're going to I sort of like this format of it, of you working on it for a couple minutes. And again, no pressure, but try to find a point of frustration. And then when we go through it, even if you don't want to say anything, sort of think about that, be cognizant of it so that you can, get as much out of the example as possible. But hopefully some of you will want to chime in. I always like it when you guys chime in. So we are given the job of designing a large horizontal ring that will rotate around a vertical axis and that will have a radius of 33.1 meters, matching that of Beijing's The Great Observation Wheel, which is the largest Ferris wheel in the world, apparently, at the time of this writing. Passengers will enter through a door in the outer wall of the ring and then stand next to that wall. We decide that for a time interval of t equals 0 to 2.3 seconds, the angular position of a reference line on the ring will be given by theta equals ct third, right? So we know theta. Where c is given is this constant, right? So we have c. And after 2.3 seconds, the angular speed will be held constant until the end of the ride. Once the ring begins to rotate, the floor of the ring will drop away from the riders, but the riders will not fall. Indeed, they'll feel as though they are pinned to the wall. For the time t equals 2.2 seconds, let's determine the rider's angular speed omega, linear speed v, angular acceleration, tangential acceleration, radial acceleration, and acceleration a, the total acceleration vector. So you should be more than set up to work through this problem, and it will cover all of the stuff that we've seen. So I would say hop to it. I'll give you till about 1:40 to do the work, and then we'll go through it step by step and look through each one. Okay? And please ask questions. Don't feel like I want to be very clear. The 5 minutes is for question asking and things like that. Now is the perfect time to ask questions on this if you don't get something. You don't have to wait for me to go over it if you don't want to either. Just want that to be clear. Okay, so this one is not too bad. So remember what I said yesterday. If you have theta or you have x, you pretty much have everything, right? So we have theta equals ct to the third power. Remember that omega equals d theta dt, and alpha equals d omega dt. So we can write that as equal to 3 ct squared, and this will be equal to 6 ct. All right, I'll make the alpha look a little cleaner here. No, stupid mouse. Tricks for kids. Okay. Alpha. All right. So all we have to do is plug in t equals, they want to know, let's determine the angular speed, linear speed, angular acceleration, and tangential acceleration for the time t equals 2.20 seconds. So we can just plug all of that in here. But before we do that, let's derive everything else. So we know that v is equal to omega r, right? And we have that as equal to, and a t equals alpha r. So from there we can see that this will be equal to 3 ct squared r, and this will be equal to this will be equal to 6 ct times r. All right, so I'm going to have you guys plug those in. and see if you get the right expressions, but you should. And see if you can get those. And then, of course, a radial will be equal to v squared over r, which equals omega squared times r, which would be equal to omega squared would be 9 c squared t to the 4th times r. And so all you have to do is you have all the expressions now. You can plug in all the numbers. You can plug in for any t. You can now solve in the interval from t equals 0 to 2.3 seconds and get all those quantities very simply. So get them for a little bit, and then we'll tackle the next part. I'll give you about till 1:45. Well, let me see what the seconds look like for 1:45. I'll give you a full minute. I just want to be sure it's not gonna. Yeah. So I'll give you till basically 1:46. It's only 15 seconds to 1:45 to plug those numbers in and get an idea. You don't have to tell me what they are. R is the radius, right? So remember the radius of the Ferris wheel. The radius is right here, embedded in the problem. Yep. I know. It happens. Okay. So in order to, the numbers are useful, and I know we all like them. Let me. That sounds about right. You said omega. I have here omega is equal to 0.9. I have the tangential acceleration. Hold on, I have the numbers here somewhere. They're kind of floating all over the place. I have omega equal to 0.928 rads per second, not 30.71. Oh, you meant alpha. So alpha here they have is equal to 0.843 rads per second, but they do have the tangential acceleration equal to 27.91. So you're right on AT, but I'm wondering what you're looking at there if you multiplied something wrong for alpha. So at any rate, let's take a look at Yeah, I'm not sure because the 27.91 for AT, the tangential, is correct. But the 30.71 for alpha, that seems too high. And if you multiply 30 by 33.1 meters, that's not going to be 27.9. That's going to be close to 900. So, I mean, it's at least, yeah, alpha 0.91 is closer to alpha. I mean, that's a little high, but that's, that's okay. Omega is about 0.928. So if you're talking about omega being 0.9, that's right. So I'll write them down. Omega is equal to 0.928. Alpha equals 0.843. Okay. I was hoping we wouldn't have to relegate ourselves to numbers, because even though the numbers help us check out that we have the answer, they're not really, how shall I say, they're not really useful for looking at the behavior of the system. Okay? So we can see, for instance, that just by looking at this, and what I mean by that is look at the two accelerations. Which one of these accelerations is going to have a bigger impact on the overall motion? Look at the tangential and the radial acceleration. As you go from 0 to 2.3. We're looking at the accelerations right here. All right, just look at how they depend on t. It should jump right out at you. Because remember, AR is equal to omega squared, right? So omega is equal to 3ct squared. So 3 squared is 9, c squared is c squared, and t squared is t to the 4th power. And then so we put that here for AR, we have v squared over r, or equals omega squared r, and we just plug it in here. And what you can see, what I'm hoping you see, is that the tangential acceleration depends only on t, is linear with t, but the radial acceleration will be the far more dominant term because it depends on t to the 4th, right? So that is a much bigger term than t. So when we look at this, to do the last part, right, here to get the magnitude, the numbers are probably okay. You have AR. I'm going to have you guys check the numbers on the book, because I kind of didn't want to write the numbers down to stop checking the numbers, and I kind of told you I didn't want to look at them. So I'm not going to verify, but if that's what you got, then I'm going to say it's right and okay. But you know, I'd say if the rest of the class gets it, Archon, you're in good shape. And if not, then you guys can talk about it during break or something. But there's just too many numbers to verify on this one, when again, the numbers aren't as instructive, right? So what's more instructive is the behavior of each of the variables as a function of time. You'll notice they all depend on time. And so the number for A, right, whenever you find plus AT squared, you can find that way. But what's a little more interesting is the tangent. And in order to set up the tangent, we want to set up our little diagram here, and we'll look at a spot in the circle, right, where we can make a nice XY axis. So this way we can very easily at this spot write that tan theta equals AY over AX, and that will equal AY will be the tangential over AR. in this particular case. Okay? So when we look here, when we look at the tan theta function algebraically, that's going to be equal to, let's see, AT we have as 6CT, 6CTR, right, over the radial acceleration. Hold on. Oh, we lost in numbers here. Over 9 c squared t to the 4th r, right? And that's going to simplify to 2. This will cancel with one of those. This will cancel with one of these. And the r's were canceled. So it'll be 2 over 3ct to the 3rd. And there we can plug in and we'll get we can take the arctangent of this expression. And there I'll at least, if you've done everything right, you should get theta equals 44 degrees. That's how you can check. That was the only number I wanted to give you. Or 44.4. Okay? So we can see here, looking at it, you know, that the radial acceleration is dominant over the tangential acceleration as far as time dependence goes, and get an idea of how it swings. Again, remember the goal is to understand sort of how the object is moving. The numbers don't illuminate much to that effect. So let's go on and start talking about our next topic, unless there are any questions on this one, besides the numbers. What are you all thinking? Yeah, practice goes a long way. But just keep in mind for here, I want to go over the structure of the problem again before I move on. So hopefully that will help when you do practice. Remember, everything is given with this function theta equals ct. From there, we were able to take time derivatives to get omega and alpha, and we could use our linear to rotational expressions to get v, the tangential acceleration, and the radial acceleration, right? And so that gave us our terms. All we have to do is plug in the radius, which is here, the c value for the constant, and then it asks for you to evaluate everything at a time equals to 2.2 seconds. So that's just plugging things in, and that's why I'm a little, you know, I got a little salty about going over the numbers, only because it's just plugging in. It's like, did you plug it into the calculator right? I don't know. If you got the, you know, if you plugged everything into your calculator right, you'll have gotten the correct final answer for theta, right? But you know, that's basically all we're doing here. Now, to get the acceleration of the acceleration vector, it can be helpful to pick a point on the circle where we have a right-handed oriented axis, right? And then we can look at the acceleration here, AR plus or AT squared, like both of those are squared. So that's just regular finding the magnitude of a vector, and that's pretty easy. But then with the tangent, you know, we can just put the functions over each other and, you know, also have a nice result to look at. But that also gives us some insight into the fact that, you know, sort of directly, that we can see two things. One, the angle does not depend on the radius. So that's one interesting thing we can see. And the other is that the tangential acceleration is far less dominant than the radial acceleration. Okay? So that's all. That's the kind of insight you can get by looking at everything algebraically. So I hope the structure of the problem at least makes sense. And yeah, no, you'll need to practice. The homework should be coming out soon for this. I have it all set to auto release, but I'm hoping it's out already. And the future homeworks will be due June 12th at midnight. So that will be after the final. So you'll have time to make up if you have extra time, or to finish any extra credit if you're like, oh no, I could use the extra credit for the vectors. But please be aware that grades are due the next day. So June 12th at midnight is the end. It's the final cutoff for stuff. So keep that in mind. We're going to decide that after the second exam. But it'll probably be during finals week during that time. Okay, so let's take a look here, and let's go forward. So now you'll notice that we've gone through kinematics. We didn't quite go through a force equivalent, but we're going to go through an energy equivalent. We'll go through the force equivalent later. But we want to develop the equivalent of mass. So we want to develop rotational inertia. And it's actually easier in rotation. It's more logical after you develop inertia to develop kinetic energy than it is to jump to forces. So we're still going to do our analog of forces, which are torques, in this chapter, but we're going to do our energy part first. But in order to do energy, right, we have translational inertia. Hold on. I'm going to do it this way. And I'm going to change the color because this is... So translational inertia sounds like a complicated topic, but we deal with it all the time, and we call it mass. All right, and so now what we need to do is come up with rotational inertia. All right, and there, right now, we have a question mark. So we're going to develop that and see what we get. So let's look at our steps and go forward. This did not... that's the thing, is I can't move these, and in my slides this is all fine, but let me just make sure that the sentence being covered up is not something important. And we will develop this. Okay. All right. So what we want to do is, if we have a system of particles, let's look above. So say we had a system of particles, right? Now, we want to, if we look at this system, I'll make a circle around it, right? K system will be equal to the sum of the kinetic energies of each individual particle. Does that make sense at least? All right, so when you do that, if you have n particles, K cis, make it better, K, just equals the sum of the kinetic energy terms, right? For I equals 1 to n. All right? So that's essentially what we have here, except that they're using our basic fact that K equals Ki equals 1/2 mi vi squared. Okay? So when we do that, we just sum, this summation is just summing all those individual particles, and then that gives you K for the system. And that gives you this, this equation here. All right? So different linear, so what we can see is that these particles, if they're rotating, will have different linear velocities, but they should all have the same angular velocity for all particles, but possibly different radii. All right? So we can write the terms of the velocity here in terms of angular velocity. So we can write, let's look at our system again. So we can say that K system equals our sum of 1/2 mi vi squared. And we can replace that. Remember that v squared, right, will be equal to omega squared r squared, right? Or omega squared times r squared, however you want to do it. So we can look at this, we can rewrite this as the sum times omega squared. Remember, the radii might be different, so you have different speeds, vi squareds, right? But your omegas will all be the same. As we talked about, everything has the same, if something is spinning, you have the same angular velocity everywhere. We talked about CDs and optical discs yesterday. The artwork doesn't get messed up. Therefore, everything has to rotate at the same way. Now, I want you to notice something here when you look at this. You have this 1/2, and you'll notice that things with the, you have these two objects with subsets here. You can have, or subscripts with the i's, and then you'll notice you have your velocity term, your radians per second term squared. So when we're looking at this sort of one-to-one, we can see that the summation of our indexed quantities here will be our inertial term. So we want to get that 1/2 out of there, and we want to relook at the equation which we've written down, which you can see is written down a little more cleanly here. But you can take the 1/2 out of the sum, and you'll notice here you have what looks like an inertial term, right? You have 1/2 for translational kinetic energy. You have 1/2 times your inertial term times your relevant speed term squared. Here you have 1/2 times your relevant inertial term times your speed term squared. So we're going to call the sum over the particles, the mi/ri squared, we're going to call that capital I. And this is going to be the moment of inertia, all right, about a rotational axis. Remember that the axis always has to be specified, because for different rotational axis, you will have a different moment of inertia or a different rotational inertia. But I is going to be equal to mi/ri squared. And you'll notice that that is relevant here with the r dependence, right? So if you put your rotation in different places, that moment of inertia will change, right, depending on its distance from that rotational axis. So this caution part here is very important. It must always be specified. And again, we'll call this uppercase I, and we'll call this the moment of inertia. Now, you might notice that this could probably get very complicated very quickly. And in fact, we will see that it does, but not quite yet. We'll see that in a little bit. Because right now we're still talking about point particles. When we talk about rigid objects, those sums are going to become integrals, and minds will be blown. But I want to talk about, I want to get to the next checkpoint, and then we'll sort of do that over break. So that's, I know we're going a little long before break, but we'll get there. We'll just have a shorter second half. So once you can do all that, right? Once you have this I term is your rotational inertia, you'll notice that your kinetic energy term can be written as 1/2 times the inertia term times the relevant speed term part squared. All right, and then you get that your kinetic energy is 1/2 I omega squared. So you'll notice you can use these equations for a finite set of rotating particles. For a rotational rigid body, you will just have to find I. You can actually still use this equation. It's just that using the only part, this is still true for rigid bodies. What you have to figure out is your moment of inertia. Figuring out moments of inertia is hard. No other way to say it. Most of the time, I'll expect you to just look them up in a table, to be perfectly honest. But there's some really interesting theories and tricks you can do with moment of inertia that almost seem like magic. And we'll cover some of those today. Rotational inertia will correspond to how difficult it is to change the state of rotation, just like a linear mass tells you how hard it is to get something moving or to pull it, right? Push it or pull it, right? It's much harder to push a train than a baseball, or a square box of printer paper if you're looking for similar shapes. And we understand that by their different translational inertia. All right. So if you look here, it's easy to rotate along, and you can see where axes make a difference here. If you look at this figure, it's easy to rotate the rod about this axis, right? This is a much easier rotation than this. You can still do it, but it's harder. And we'll understand that this rotation, this axis, will have a higher moment of inertia than rotating about this axis. All right, you'll notice that the r squareds, you can see that because the m, that should be intuitive, right? Because if you look here, even though it's not a system of particles, I is equal to m, the sum of mi r squared. Right? So that looked really bad. Right? So you'll notice that the radius is very short here. They're both the same mass. If you look at them, you'll add up all the mass the same way to get a total m. But you'll notice that this has a much smaller radius to get to from the rotational axis, no matter where you are. But here, you can get much farther. R can be much bigger here, right, than it is in part A. So you can sort of intuit that larger R's will mean that I here, I at B is greater than I at A, making it harder to rotate. Okay? So we have a figure here that shows 3 small particles that rotate about a vertical axis. The perpendicular distance between the axes and the center of each sphere is given. So you want to look at that axis that goes to the center of the sphere, not the edge. And we want to rank the spheres according to their rotational inertia, which we conveniently have the formula for here. So rank them to see which one you have the 3 spheres according to their rotational inertia about the axis. So we'll call this sphere 1. This will be sphere 1, sphere 2, and sphere 3. So rank those, and we'll start around 3:30, or not 3:30. Don't note 2:30. Sorry, misspoke there. We'll come back in about 15 minutes, and we will continue our discussions. Like I told you, this chapter is a long chapter, so I do not expect for us to finish it. I had not planned for us to finish it today, but we're making a very good stab in, and so I imagine we'll finish it probably midway through the next lecture, but I'm hoping we get through. We might get most of the way done. We might get most of the way done. So we have a lot to discuss with the moment of inertia. All right. So I will go away, and I will be back. Like I said, around probably a little before 2:30. Okay. I'm back. So anyone have any insights into the checkpoint? All the same? Let us see. So we just plug in each one, right? So 1 will be, m will be 36 times 1 squared, right? So, oh, we have disagreement. So this one will be 36. We have 2 times 9 squared, or, oh no, wait a minute, sorry, mass, 1 meter. This will be, the second one will be 9 times 2 squared, which equals 9 times 4, which is 36. Uh-oh. So 1, 2 greater than 3. Let's look. And then we have 3 times 4 squared, which is 16. Oh no, 4, yeah, 4 times 4 is 16. No, see, I'm doing this backwards. I am getting confused. Like, I know what I'm saying is wrong. Yeah, Artin. You're yeah, I'm doing the big reveal here. They all are going to be the same. I'm just keep getting it mixed up in my head. I do that sometimes. So let me do it slowly. So the mass here is 4 kilograms, right? And that's going to be times the distance is what gets squared. That's going to be times 9. And you'll notice that again is 36. There we go. Now I'm not going crazy. Yeah, no, me too. Yeah, no. It's m, right, times r squared. These are the r's, and the m's are given here. These are m's. But in my head, I was mixing. I mean, in my head, I could read it, but I was mixing them up, which I do sometimes. So, and I was going, no, that's crazy. But yeah, but Artin is correct. They are all the same. So, and a few of you, yeah, Gian got it as well. So yeah, no, there's no reason to apologize. It's the checkpoint. We're supposed to learn from it. So you can see here that you'll get the same inertia. What this is supposed to show you is that unlike mass, where like 5 kilograms is 5 kilograms, you can have a lot of different situations. Let's clear this up. Give you the same rotational inertia. Okay. So rotational inertia is a little more difficult to wrap one's head around. So you'll get here, they're all equal, yay! And now we want to look at calculating rotational inertia for rigid bodies, or we want to build up to calculating it for rigid bodies. Or no, I think we go right to rigid bodies. Hold on. Yeah, we go right to rigid bodies. So as you can see here, that sum becomes an integral. So let's start with the sum and look at what's happening. So when we look here at I equals the sum of mi ri squared, right? So your distance from your value, we already sort of have this varying distance. The question is when you make a solid object, is the density uniform or non-uniform? And so when you look at it at a very small bit, the distance from r will be usually fixed, right? You look at different r's, but you'll have a small piece of dm. So when you look at I, in order to get I, you're going to add up a whole lot of little delta m's that are some distance away from the rotational axis, right? There'll be a fixed distance, not a differential distance. You can think of it this way, right? If you look at a whole object and it's rotating about this point, so this would be a bird's eye view, right? So this thing would be rotating like this. In order to make this easier, you'd break it up into small little pieces, right? But if you take any arbitrary small little piece, it's going to have a fixed distance, r, to the rotational axis that won't necessarily be infinitesimal. That's why it's not dr, right? But you will have a small little piece of the mass, m, and what happens is you will add up all those little pieces of mass, and so when you take the limit as those dm shrink, you will get that I is equal to the integral of r squared dm. Now the dm differential can seem like an enormous pain in the rear, and it is. But remember, when we have a dm, actually, no, you don't. You might not remember this, but when you have a dm, you can turn that into a density, because remember, density is equal to m over v. And remember I told you that it's going to be very more powerful that it's equal to dm over dv, where this v is a volume integral. So we can change this to the density rho, which is constant, right, times dv. And volume integrals are spatial, and we know how to deal with those a little bit better. So dm will generally, in one dimension, right, in a linear dimension, will just be one dimensional, and the integral will be easy. But typically, this would be dx, dy, dz. All right, and you'd have to do what's called the triple integral along each differential to fully integrate to get the moment of inertia. So this becomes difficult because to really fully describe the moment of inertia for an object, you want to look at its principal rotation axes through its center of mass. And that gives you something called a inertia tensor, right? Which is equal, so it has 9 entries, A, B, C, D, E, F, G, H, I, right? And you can eventually find that the tensor has to be symmetric so that these 3 entries are equal to these 3 entries, okay? But each of these entries here in this matrix, right, each one is a triple integral. So it's, you know, finding the inertia tensor is hard, and so those triple integrals are often not trivial. So, you know, you want to be, you know, the point here is we're going to sort of stop at this area, and in order to do this calculation, we need a lot more machinery than we have, and it gets pretty complicated pretty quick. But that being said, we're just going to use the results of those very difficult calculations and just have a table of moment of inertia. So hopefully you're all breathing a sigh of relief. This is usually fun for me in class because I can see the tension growing when I go over how hard it is to calculate a moments of inertia. And then when I show the table, everyone just goes, ah, it's not so bad. So it's not so bad. You basically just will use this table. All the shapes you'll deal with will fall somewhere in here, and you'll be able to calculate them pretty easily, or just look them up. But we will look at a few simple examples just to see how some stuff works and use this table as a reference. So you'll notice that you have, you can see the moment of inertia for, so for instance, for our long, thin, our rod, our cylinder, versus these two sort of equivalent shapes. And we sort of claim that this rotation of inertia would be a lot bigger than the other one. And so, so you'll notice that there's 2 m's, and you have this L squared, and L is generally much longer than R. So even though it's 1/12 here, all you have to do is get this to be, you know, more than, you know, get this up to 4 to equal it. But you'll notice if you have a small length, you really just have a disk. And so a solid cylinder or disk. So usually with the disk, you'll just ignore this part of it. It'll be a thin disk, and you'll have the, you know, you have a circle or something like that. You know, you really won't have to deal with it that small. But you can see there's a whole other term here. Okay, so this is a thin rod in which the radius doesn't matter, right? So then this part is so thin that this part goes away. You get the 1/12. And you'll notice that some of these look the same but are different, okay? All right, so let's get ready to rumble here and let's go forward and look at some applications. The most important application of the moment of inertia or extension is this parallel axis theorem. So what this does is it makes this very difficult process that I told you about into something simple, and it almost seems like magic, but I promise you, if you do use the parallel axis theorem and then go back and solve for the same moment of inertia from first principles, you will get the same thing. It will work out. So it also puts an emphasis on what I told you, that center of mass moment of inertia. All right, so making 3 axes around the center of mass and then creating a moment of inertia tensor. So if we know the moment of inertia for the center of mass axis, we can find the moment of inertia for a parallel axis with the parallel axis theorem. All right, so if we can find ICOM from the center of mass from, say, that table, or if it's just given, we can, because if it's too hard, we'd have to calculate it numerically. So if we have that, so if you look at this weird shape here, we have the center of mass here. If we just add this plus m, where this is the total mass of the object, you'll notice that you just have to add, if you add this new point here, right, h, if you move your axis here, then that that axis of rotation at P is parallel to the center of mass. Both of these are coming out of the board and pointing right at you. If you're looking at your screen, you can imagine both of these coming out at you, and they're parallel. So we have to note that the axis must be parallel, all right? And the first must go through the center of mass. So you can't just use the parallel axis theorem to arbitrarily relate any 2 axes or any 2 parallel axes. You need to do the center of mass moment of inertia. And that's why, and the power of the parallel axis theorem motivates solving for the moment of inertia first through the center of mass. Because once you have that, you can just go through and find these and then the parallel axis theorem makes it easier. We'll of course look at it for a trivial example, so that we can whatchamacallit, we'll do the checkpoint, we'll look at, and then we'll look at it for trivial examples so that we can understand that the theorem works, we can sort of see it. But then, of course, when situations gets complicated, we just stick to the parallel axis theorem. Okay, so let's look at this checkpoint. We've got a book, and you'll notice we have these axes, different axis rotation, and they're all perpendicular to the face of the object. So we want to rank all the choices according to the rotational inertia of the object about the axis, the greatest first. So we're ranking moments of inertia again, but we want to go and see which ones we have, or which ones are greater. So you have 4 axes, 4 moment of inertias. All right, so let's take a look at, you'll notice that all these axes are parallel, and I'll write down the parallel axis theorem, as that will be your guiding light. So the new moment of inertia will be equal to the moment of inertia, COM, plus the total mass times h, where the distance would be away. So this one's at the center of mass. This one will be h4, h2, and then this will be h1. So hopefully you can figure out which moment of inertia will be the greatest. I'll give you a hint. They're not all equal this time. So we've got one answer, 3421. Three, four. Right, greatest first. So it would be 1, 2, 4, 3, right? The key here is H. So all you have to do is look at these distances, and you can tell by inspection that H1 is greater than H2, is greater than H4, which is greater than 0, right? Because remember, the H here is 0 because you're at the center of mass. Okay? So because this is true, and you can see that by inspection, each of these H's gets plugged in here. So because of that, I1 is the greatest, right? Is greater than I2, is greater than I4, which is greater than I3. And keep in mind that I3 is equal to ICOM, center of mass, moment of inertia. Okay? Does that make sense? Okie dokie. Now, let's look at this for a little bit more complicated of an object. All right? We have a rigid body here, right? So we have, you'll notice we have the center of mass is given by the X that I'm highlighting. And I'll just point to it. We have a dot here by the X. And you'll notice we have two rotations. So we have this center of mass rotational axis, and we have this this rotation axis through the end of the rod. All right, and we can calculate the, if we know the center of mass moment of inertia, we can calculate using the parallel axis theorem the moment of inertia here. But I want to do these both by first principle, and then we'll look at the parallel axis theorem in the next slide. So let's do them both by hand, because I want you to see how the parallel axis theorem gives you the same answer. So if we look here, we'll just do both of these. So you'll notice they're connected by a rod of negligible mass, right? So we can treat this rigid body as two objects. So we'll go back to our point definition for this, right? I is equal to the sum of mr squared, right? So if we look here, we have our rotation axis. So this will equal m times L over 2 squared, right? I'm just doing this by exhaustion. I get one particle, and then the other particle is the same, m L over 2 squared, right? So this is going to be equal to 2 times m L squared over 2, which is of course incorrect. You should see that as wrong because we have to square that 2. So we got to get 4, and that's going to be equal to m L squared over 2. All right, so for this one, I equals ml squared over 2. Okay? Does everyone see that? Does that make sense? Good. Now let's do it for the one down here. So you'll notice this one's a little different. We have, if we look at our two terms, we have the first one is m times, we're at the axis of rotation here, right? So now we're going to have, I wish to delete this m, I just spoke too soon. Now we wish to have I hate having to select this stuff. I equals m times 0 squared, so that'll be 0, plus m times L squared. So that's just going to be equal to m L squared. Okay? So, do both those make sense from the point particle expression? So what we've done here is essentially we've looked at solving these by definition, right? The center of mass one was easy, and to be honest, this one was easy too. But we want to check and make sure that the parallel axis theorem makes sense. Okay? So you'll notice here, as we look through our example, we have that by particle, we get ml squared just like we did before. But now let's use this ICOM. All right, so I know it's written here, but I'm going to write it each step down. So as we saw before, ICOM was equal to 1/2 m L squared, right? We got that. And now we want to move the axis from the center of mass to m over here, right? So now what we have to do is we have to add the total mass of the system. So that's going to be plus (2m), right, times L over 2 squared, I believe. Yeah. Right? L over 2 squared. Okay? Because that's the distance we moved here. We move the axis this distance h. That's all it is. The distance from the center of mass to its new location. And we can see from simplifying this, right, we get equals ml squared over 2 plus 2ml squared over 4. So that's going to become 1. That's going to become 2. And 1/2 plus 1/2 is equal to 1. So this will be equal to ml squared. All right, so you can see that the parallel axis theorem gives us the same result as summing by the particle. Now in this case, it looks a little, it looks like it's more work, but again, that's often how these things go, right? This method of doing things will quickly become more difficult, and as the systems become more complicated, it becomes more and more and more and more difficult to calculate. This always stays at the same level of difficulty, right? So it's not much more than an addition problem, and it remains an addition problem, whereas this can become more and more advanced and difficult to do. If you ever have to, if you're ever in a position where someone asks you to calculate the moment of inertia for a cone, you will see what I'm talking about. That is some hard stuff. All right. So I think so now we're looking at a so now they're looking at the rotational inertia of a thin rod, right? So now instead of points, we have a thin rod here, and you'll notice that we take a little part dx dm, and then we'll use the integration method to add all of them up. We already sort of went over this. I'm gonna have to move this slide in the future because we already did this. But it probably just makes more sense going along with what we looked at before. So the next thing we want to do now is, now that we've talked about energy, is we want to talk about our force equivalent, which is torque. All right? So we're going to notice that torques occur, and this goes back to where free body diagrams are going to be a little harder, because we'll have a rotation axis, right? It may or may not be at the center of mass, but you'll have a rotation axis. You will have a center of mass somewhere here, but you'll have the point at which a force acts on the object. And so this fixed force will have a tangential component. All right, so you see how this force can be broken it acts at this angle phi with respect to this rotational axis. This is usually called the line of, well, this isn't the line of action, but this is an extension of the rotation axis. In engineering, you'll usually use the line of action and the moment arm to create this right triangle from where the rotation axis is this distance from the rotation axis to the point the force acts is the hypotenuse. And then if you extend that force, if you just extend the line of force, that's called the line of action, right? And then if you do the perpendicular distance, that's called the moment of F, or the moment arm of F, all right? I usually don't use this language because it gets confusing for me. I do torque as a physicist, which means that I'm always looking for torque to equal R cross F. So I'm usually looking for R, F, and the angle between them, right? So R, you would extend out here, you get this angle phi, and then I just calculate the cross product directly. Engineers seem to like this way of thinking. It helps them, and you're going to learn that in statics a lot too. They're going to use this way of doing things, which is more than fine. And you can do it. I can understand it if you do the work and do it correctly. I can read it. I just don't like doing it that way. But we'll see. We'll sort of see these pop in and see equivalent forms of torque and things like that. But what I want you to notice, getting back to the physics, is that you have this radial component of force, and then you'll have this tangential component of the force, right? You can always decompose it into those two directions. Let me get to the pointer, right? You can see that here. This is FR. It extends from the radius, and then you'll have this tangential part. So this tangential force, right, will lead, acting at this point P, will lead to a rotation. And so in order to quantify that, we call the force acting on, acting this distance away from this axis point, that is called a torque. And you can see they won't give you this definition, I don't think, till chapter 11, but this is the good definition of torque. This is always how I picture it. So you're gonna note that they're gonna build up the magnitude though first by saying that the torque takes these factors into account: the R, the F, and the sine of the angle between them. And they're gonna ask you to sort of notice that this is from chapter 3, the magnitude of a cross product. But we won't really get to that till chapter 11. So again, here we're defining our line of action and our moment arm. The unit of torque, it does not have its own special unit. It is a Newton meter, but we want to note that a joule is a Newton meter, but torques are never expressed in joules. Torque is not energy. And in fact, torque, more importantly, is a vector. Energy is a scalar. Okay? So we have that important distinction. Where's my? Oh Lord, I don't know where my phone went. Oh, there it is. Attendance. Okay. Oh dear. All right. I just need to set this up for a second. Hold on. Well, we have a checkpoint, so hopefully we're reading that. That's not working. Okay. So, all right, let's, sorry about that. That was a brain fart there. So torque is positive if it causes a clockwise rotation. So I don't know if you can see my hand here, but if I move this and I cause torque is positive if it causes a counterclockwise rotation, right? So if I'm moving, at least this looks to me to be counterclockwise, the mirroring might mess everything up. So get something on put your hand in front of your face and push a force up, and that'll cause a counterclockwise rotation. If you push down, it should cause a clockwise rotation. The mirroring from the camera might mess that up in particular, so don't worry too much about it. But let's, if you have several torques, all right, if you have, so basically if several forces act at several points to cause individual torques, you can find that the net torque, right, the net torque is equal to the sum of the torques. Okay? So let's look at our checkpoint. We'll clear that up. So the figure overhead shows a meter stick that can pivot about the dot. So you'll notice there's only one dot. It's right here. Okay? So there's 5 forces acting on the stick. All right? All 5 forces on the stick are horizontal and have the same magnitude. Rank the forces according to the magnitude of the torque they produce, greatest first. Okay, so I guess we're looking at a bird's eye view. That's what they mean about horizontal, because clearly they're in different directions. So let's take a look at which one of these give the greatest torque. All right, so you want to recall the equation that they give us for torque is that the torque, the magnitude of the torque, is equal to RF sine phi. All right, and we only have one rotational axis here. So take a look at that and see if you can figure it out. Well, we want to be careful because if you notice, if we look here, we should be able to tell which ones are 0 first. I always like to go to the least. All right. So if we look here for F2, R is 0, right? And for here, for F5, sine phi equals 0, right? The angle between, you always have to look at, the trick is to making effective, I'm going to use a different color, is to make effective R vectors. So you want to remember your R vector is something you want to draw all through and have it go this way. So the angle between F5 and R is going to be 0. Sine of 0 is 0. So that means F5 equals F2, right? And those are the smallest. Now, if we look here, we can see that F1 and F3 are going to be the same, right? They have the same R vector. And we're looking at magnitude, so the direction doesn't matter. And the magnitudes are the same, right? So we have the R's are the same and the angles are the same. So we'll have F2 or F1 equals F3. Now, does F4 fit in the middle or somewhere on which side of this does F4 go? Now, F4 will have the same F and R, right? So RF won't change, but you'll notice that sine of whatever phi is will be less than sine of 90. So that will put F4 clearly in the middle, and we can delete this comma. All right. So I think that's a good enough place to stop for today because we have a little bit more. We're almost done with the chapter. So I'm pretty impressed with how far we got today. I honestly didn't think we'd make it to torque. I thought we'd end right as we were beginning torque, but we had enough time and I thought we did a fairly good job with it. So we will wrap this up on Tuesday, and then we will move to chapter 11. So I'd sort of anticipated that we would get through Tuesday, right? Yeah, because, oh no, wait a minute, I'm sorry, this is Physics 1. We'll do this Thursday, right? I got you confused with the other class. So I'm going to stop the recording so I don't forget to stop the recording.